we need to decide what does the term learning mean. We need to decide what does the term possible mean. And there are many ways to do this, and I will tell you what are the ways we are going to focus on today. And so here are a few options for models, for definitions for the concept of learning. There is the PAC model, which is maybe the most famous one. There is an online model of learning. There is a statistical query model of learning. There is some model that we suggested a few years ago, which we called universal learning. There are many models. So this is one type of questions, models we can choose. And on the other hand, you can try to answer this question for specific algorithms or specific ways to learn, like neural networks or other mechanisms. And I'm not going to talk about this type of research at all today. So the talk will be very high level and not specific. So these are just some options. And I want to tell you, just to introduce some symbols. So the type of data we are going to deal with is the data points we get as people who try to learn are points of the form x and y. X is an element in some domain. In this example, x is a picture, and y is the label of the picture. In this case, it is 0 and 1. So these are the data points we are going to get. And what we want to output as a learning algorithm is predictions on data we did not see so far. And in this talk, the way to model it is to find a function that maps every picture to its label, to some label. So the output will be some function of this sort. Is it okay? Good. So this is just introduction of symbols. And now the first definition, which is a choice, the first definition is what do we mean by a learning problem? Okay, so what is the definition of a learning problem? So in this talk, and this is a standard choice, we are going to think about a learning problem as a collection of functions, which I will denote by H. And there are a few ways to think about this collection of functions H. It is sometimes called the hypothesis class. And so it can be thought of, this class of function, as the outputs of the algorithm we are going to use. So the algorithm we are going to use is outputs some functions as one function in some collection of functions. So we can think about all of these functions the algorithm can output as the class H. One perspective. The different perspective is we, the algorithm developers, can do whatever we want, not related to H, but we think about H as the thing we want to compete with. So H is the standard we want to be above or below, it depends on your perspective. We want to beat. So this is a different perspective. And the third perspective of this H is not about the output of the algorithm, it's about the way the input is collected. So we can think about this H as the context of the problem, where the data is coming from. So these are three different perspectives on the same object, which is just a set of functions. And so you can choose whichever perspective you wish. I'm not going to talk more about this. One more mental picture which is useful, I think, is this collection of functions can be thought of as a matrix, a big matrix. The rows of the matrix are the functions. The columns of the matrix are the points in X, the elements in the set X, the images. And in the position HX, there is a symbol from y, which tells us the value of h on x. So it's a big matrix. This is another mental picture that is useful. Is this okay? Do you want to ask something? Okay. Now, there are many choices for structures that we can think about. So let's, both the domain X, say the collection of pictures, can have some structure, like there is some, it could be in a geometric setting, it could be an algebraic setting, there could be some symmetries like translations of images. There could be many structures that one can put on top of this to try to understand it better from a mathematical perspective. In this talk, I'm going to ignore any structure and focus on the scenario where when there is no structure. So X is just some set and Y is just some set. This is the framework I'm going to consider. Adding more structure is very interesting and maybe very a very good thing to do, but I'm not going to do this here. So this is another comment I want to make. Okay. So now we have a question that is a bit closer to mathematics, is what properties of this learning problem H allow us to solve the problem? Okay, so this is a bit closer to a math question. So at least we have a class of functions. And the way we are going to answer this question in this, I'm going to tell you one way to try to answer this, is using dimensions. So there is a rich theory of defining dimensions for such concept classes. And I will tell you a bit about this, this idea, this mechanism. So what is a dimension in general? A dimension is some way to assign objects numbers. And the essence of this number should be that the number should be high if the problem is hard or the object is complex, and the number is low if the object is not so hard or less complex. So this is the high level thing we want to achieve. And there are many ways to define dimension in various contexts in mathematics, in algebra, using a metric structure. And again, I'm not going to use any of this today. So we are going to talk about an unstructured setting. So there is nothing we can do, like there is no operation that comes with X or Y. So it's a good thing because we have very few things we can do, but it's a bad thing because it's a very general scenario and maybe it will not prove the correct statement in reality. But this is the setting I'm going to focus on. So we are going to talk about dimensions of a learning problem H in a scenario when there is no structure. So there are some good things here. So such a theory can help us understand things better and can help us choose things better in reality, make better algorithmic choices. But there are also some bad things here. It could be too general to be related to reality. And specifically, the type of estimates we are going to see is very far from reality. But this is a theory. It has good things and bad things. So. Yes. Yes. So right now it was sort of general, some complexity, and in this scenario, yeah, the thing we are going to try to capture is sample complexity. But I will not even say this very concretely. Yeah. Okay. So the type of statement which we are going to talk about is this type of statement. We have some notion of learnability, which is one of the notions we saw before. and we want to find some dimension that captures this learnability in this sense. This is a qualitative statement, and you can ask for a more accurate statements, but again, I'm not going to be very accurate here. I just will give a high-level picture. So this is the type of statement that we are going to seek or see in various contexts. So far, the line is okay. And I'm going to tell you about 2 ways to define dimension in this unstructured setting. One type of dimension is to measure things locally. I will explain in what sense. And a different perspective is to use computational complexity as a mechanism to define dimension. So these are 2 ways to define dimensions. So what does local mean? So the thing we can always do is project. So we can always choose a subset S of X and take all functions of H and restrict them to the subset S. So we can project H to S. So this is an operation that is always available to us. And then we can measure local complexity. Complexity just on the part related to S. And the standard way to talk about complexity in this way is using a notion called shattering. So shattering is complex in this context. And after we do this, the dimension is automatically defined. It will be the largest set, the size of the largest set that is shattered. So we look on local parts of X, see what happens, and see what is the largest complex area in X. This is one mechanism, which I call local complexities. This is one mechanism. A second, so this is, I think, is relatively well known, this mechanism. A second mechanism, I think, it's not usually said in this language. So here's a way you can use computations to define dimensions. So to define a dimension, we choose a collection of functions that I denote by G. So these functions take so every function in G takes a function H as an input. So G is a collection of functions from Y to the X to some target space L. L is, in the example below, the set of leaves. So L is some set. And this collection of functions is graded by cost. So every function has a cost associated to it. This is the computational complexity of that function. A specific example, when the class, when Y, can you see this? Yeah. When Y is just 0 and 1, we are just looking on binary classification. A specific collection of functions is the collection of full decision trees. Decision trees, so that every vertex has either 2 vertices going out or none. And the vertices are labeled by x's, by elements of x. And all the leaves have a different name. So there is leaf number 1, leaf number 2, leaf number 3, leaf number 4. So this is a specific example for a collection of functions from 0, 1 to the x to, in this case, the numbers 1 to 8. Does it make sense? Not so much.
So you map a function to a leaf?
So a function G is captured by this decision tree. When it gets a Boolean input, it goes along the tree until it reaches a leaf, and this leaf is the output of the function on this input.
Map a function to a leaf?
Yeah, so a Boolean input is a function from x to 0, 1, right? Every x is assigned either 0 or 1. So it's very, I'm very sad to hear that. I'm really, I became, so 0, 1 to the n is n bit strings. So a function from 0, 1 to the n to L.
So electronic graphic in this example is A1 to the end functions. G.
So maybe I can ask the following question.
Yes, yes.
Is the class G that you're taking the example of just decision trees here? Looking at the class of all functions which are decision trees?
Full decision trees, yeah.
Right. And then maybe the depth or something is the complexity measure you assign to each?
Yeah, exactly. The cost of a function G in this class is the depth of the tree. Yeah. Does it make? Yeah.
So here you pick the computational model together with say G. Do you consider
G is the computational model.
okay, so we define the computational model and this is the class of function.
Yeah, the computational model is a class of function, and each function in this class has a cost, its computational cost. And using this collection of functions, we can try to define dimension. This is but so far I did not tell you so the first step is to choose some computational model in the standard setting, except that the output of a function is not 0 or 1, it's some leaf in the tree. So this is the only tweak. Okay, so now if we have such a computational model, we can define a notion of shattering. So we can choose a map in G, one computational model, in this example, a single decision tree. And we say that this single decision tree is shattered by H, by the collection of functions we care about, if for every leaf in the tree, for every L in the image of this function, there is some specific function in H that leads to this leaf. Okay? So in this way, we can define that a collection of functions H, which in the standard setting is just a collection of Boolean inputs. So every function is like a Boolean string. It shatters a decision tree if it reaches every leaf in the decision tree. Okay, so, and then we can define dimension. The dimension is the maximum cost of a function that is shattered. So we used computations to define dimension. And the point, the thing that is good about computations is that there is no algebra, there is no topology, it always makes sense. This is the good thing about computation. Okay, so this was very high level, and now I'm going to give you some examples. I hope it will be. Yes.
So model of learning decision trees, then this means that this is the number of samples you need in order to learn H.
So there are two parts here. One is the dimension, which is some, let's say, number like 5. And then there are the models where this dimension is relevant. So the dimension, some specific dimension is relevant to some learning task.
No, I'm just saying specifically about if you take decision trees and depth.
This is related to what is called online, so I will say it soon.
Let me give the example.
So yeah, so I think, so this was high level. Now the point and the thing I'm going to do is give many examples of this idea. So, okay, so here are some examples. And let us start with the simplest setting where we care about binary classification, or y is just 0 and 1. So this is the scenario, the simplest scenario. And the most well-known example is called the VC dimension. The VC dimension assigns an integer or infinity to a collection of functions. And the notion of shattering in a local sense, we say that a subset of x s is shattered if when we project all functions to this part of the universe, we see every possible option, all functions, all Boolean functions, all Boolean values. Does it make sense? So this is the standard notion of shattering. When we project, we see everything. And then we have the VC dimension, which is the maximum size of a shattered set, which could be infinite also. So this is the first example of a dimension. It was defined a long time ago. I will say soon how it is related to learning. But this dimension can be defined by, in the computational perspective as well, as follows. So the computational model, G of VC, is full decision trees as before, but in every layer of the tree, all vertices have the same label. So this is a collection of functions, and L is the collection of leaves in the tree. And the cost and the cost of such a function is the depth of the tree. So if you think about it, this definition is identical to the VC that we saw before. It gives the same dimension. So the VC dimension can be defined locally by projection or by computations using the decision trees with a certain structure. Does it make sense? Okay. And now the VC dimension is related to learning in this way. It captures exactly PAC learnability of H. Okay, so I did not define PAC learnability. I'm going to talk about many models, so I won't define all of them. But it is some standard notion of learning which is captured by VC dimension in this sense. And I want to comment that the VC dimension is a very important quantity in general. It gives us combinatorial data on H. This is the Sauer-Perles-Shelach lemma, or Sauer's lemma. It gives us a way to understand H as a metric space. This was proved, the best thing was proved by Hausler. And it gives many, many things. So I will not talk about the more applications of the VC dimension, but the connection to learning is the VC dimension captures PAC learnability. This is the theorem that was proved a long time ago.
Yeah, so also the complexity.
Yeah, so I don't want to. So I don't want to give many details. I just want to keep it high level here. But this theorem is more informative than what I wrote. And sometimes people call it I think it's the fundamental theorem of statistical learning theory, or some version of these words. Okay, so this is a basic theorem about learnability. And now I want to tell you other theorems of this sort, which are more recent. So, this theorem comes with there are two proofs, or many proofs, but two ideas that come from this theorem. One, and both of them are algorithmic, which is a good thing. One is that if we try to minimize the empirical loss in the VC setting, this is a very good thing to do. Then we learn. So an ERM is a good choice for PAC learning. This is one important idea. And the second important idea is that there is a specific algorithm, which is called the one inclusion graph algorithm. I will tell you about it later. It's a very, very nice algorithm and completely abstract. So it can be used in many, many settings. So I will try to explain it later. So these are two algorithmic parts in this theorem, in this theory. Okay. Now I want to define two other dimensions, which I think are less known. One is called the threshold dimension. So now we have this collection of functions, h, and these are just Boolean strings, 0, 1 strings in our mind. And the notion of shattering here is we take the collection of functions, project to S, and then we want to find a full chain. What is a full chain? A full chain as a matrix is an upper matrix with 1 and zeros, if we think about it as a matrix. And as sets, it's the empty set, a singleton, a set of size 2 that contains the singleton, a set of size 3 that contains the previous set. So we have a full chain of sets in this projected. So this is a different notion of shattering, and it gives some other dimension, the threshold dimension. Okay, so this is defined by local complexities. And this threshold dimension has a friend, which is called the Littlestone dimension. So the Littlestone dimension is defined by full decision trees. This is the example that we saw before. No restriction. This is called the Littlestone dimension. So the collection of functions is full decision trees. They are graded by depth, and the outputs are the leaves. This defines a dimension, the maximum size of a full decision tree that is being shattered by this class of functions. So this is called the Littlestone dimension. So we have a threshold dimension, and we have Littlestone dimension. The first thing I want to do is relate them to the VC dimension. So the VC dimension is the smallest between all of them. So it is the least among all of them. So this is one statement. And the second statement is that the VC dimension could be 1 and the other two could be infinite. So there is no comparison between the VC dimension and these two dimensions. So these are just two simple facts. And a less simple fact is that the threshold dimension and the Littlestone dimension are equivalent in this numerical sense. So the tilde is some constant. I'm not sure even so. And so the Littlestone dimension is between log the threshold dimension and 2 to the threshold dimensions. Okay? So this was proved by Shelach and Hodges in the context of model theory in again a long time ago. For me, one of the reasons this came up in model theory is that there is no structure, just sets. How do you measure complexity of sets? There are not so many ways to do that. So they came up with it for their reasons, which I do not understand, but this was proved. The proofs, one direction is an exercise, the other direction is not an exercise, but it's not like a crazy thing. Okay, so this is a connection between all dimensions. So this is one, and the other two are basically the same up to some constants. Yeah. And the reason I introduced both of them is these three theorems. So the first theorem, which was the reason to define the Littlestone dimension, is that the Littlestone dimension completely characterizes online learnability. This was the reason Littlestone defined this dimension. So it answers the question for online learning. A more recent sequence of works showed that the Littlestone dimension actually characterizes something much more subtle than online learnability. It captures private learnability. So learning in a private setting. So this is also captured by the same dimension, by the Littlestone dimension. So these are two theorems related to the Littlestone dimension. And the third statement I mentioned, if this is not even a formal statement, the Littlestone dimension is somehow related to the learning rate. What is the learning rate? The learning rate is about trying to understand if we take more and more samples, how does the error go to zero? This is the learning rate. How fast the error goes to zero. And the Littlestone dimension is also related to the learning rate, to this learning rate. But I will not say more. So do you want to ask some question or say something about this? So the question was, what do I mean by online learning and by private learning? So these are two models of learning that I did not define. I also did not define pack learning, but there is a way to define it, so I will leave you either to find this out later or have some intuitive meaning right now. Okay. So we have the VC dimension, it comes with pack learnability. We have the Littlestone and threshold, which are basically the same. They come with online learning and private learning. Yes?
Do these first two theorems also come with a canonical algorithm, like PRF?
So the first one does. There is a canonical algorithm. The second one, and maybe one way to, the second one is canonical. There is an algorithm, but I don't think it's canonical in any reasonable sense. Sort of, it works, but in the question was, does they come with canonical, algorithms? So these are the statements about the Boolean setting, the binary classification scenario, and I want to move to a more general scenario when the number of outputs is not just 2, 0, and 1, it's some arbitrary number. So it could be the names of the animals that appear in a picture, or it could be the three-dimensional structure of a protein that is being folded. It could be something. But again, we don't have any structure on Y. It is just some set of an image can be either this or this or this or this. So this is a more general scenario. And now there are other dimensions you can define. So I will tell you about two dimensions. One is called the Natarajan dimension. The Natarajan dimension is again defined by local complexities. And it is the most naive extension of the VC dimension. So a set is Natarajan shattered if when we project to it, we see a copy of the cube. A copy of the cube is just a product set, a full product set of two things times two things times two things. So all possible values in a specific way. So formally, there is a way to assign every element of S two things, f of x and g of x, two distinct things. And when we project, we see all the products, all the possible options. So this is a naive extension of the VC dimension, the most naive extension. And Natarajan, one of the reasons he defined it is that this dimension gives us a way to at least understand when is learning impossible. So if this dimension is infinite, this is what Natarajan proved, and Natarajan and Tadepali, then the class is not learnable in the pack setting. So this was proved in the 80s, and the proof is an extension of the VC lower bound. There is no, it's basically an extension. And in that paper and later on, it was conjectured to actually characterize PAC learnability. This was part of the reason to define this dimension. So again, we're in the multi-class setting, many outputs. There is a naive extension of the VC dimension, and this extension gives an impossibility. If it's infinite, it tells us that the class is not learnable, but if it's finite, we don't know anything right now. And in a relatively recent work, we noticed that in some cases, the Natarjan dimension can be 1, but still the class cannot be learnable, and I will tell you a bit more about this later. So sometimes it is hard to solve a learning task, although it is not exactly clear why. There is no local, in some sense, obstruction. It's sort of a global obstruction to learnability. And I will tell you more about this later. And part of the thing that came up here is that there is some very general connection between concept classes, which is a very abstract thing, and topology simplicial complexes. So there is a very general connection between concept classes and simplicial complexes. And the Natarjan dimension being 1, this is some property that we saw before. It tells us that the dimension is as small as it can be. This corresponds to hyperbolicity of this simplicial complex. Really, there is a direct correspondence between these two notions. Okay, so this I will tell you again more later on. So Natarajan is a lower bound. Natarajan is not an upper bound on PAC learnability. And the last dimension I'm going to tell you about is the DSDimension, the Danieli-Shalev-Schwarz dimension. Again, it is defined locally. So we say that a set S is DS shattered if when we project, we see a pseudo cube. I see. If when we project, we see a pseudo cube. What is a pseudo cube? A pseudo cube is a finite collection of words or functions. It's important that it's finite. And what is the defining property? We choose a function in this collection of functions. We choose a coordinate, which is an element of S. Then in this collection of functions, there is a different function that agrees with F in every single entry except the chosen coordinates. So this is a pseudo cube. Every vertex has a neighbor in every direction in a high level way. So the Boolean cube has this property, but it's not clear if all pseudo cubes are Boolean cubes or not. There is some. This notion of shattering is called DS shattering. Danieli-Shalev-Schwarz, they define this notion. And it turns out that this notion, this dimension, the maximum size of a DS shattered set, actually characterizes learnability in this generality. So this dimension is finite if and only if this class of function is PAC learnable. Okay, so this was again in the same work. So these are all the dimensions I wanted to define. So we have the VC dimension. It comes with PAC learnability. We have the Littlestone and the threshold dimensions. They come with online and private. There is the Natarajan dimension, which doesn't come with anything as an equivalent. and there is the DSDimension that comes with PAC learnability in the general setting. Okay, so these are all the dimensions and their connections to learnability. You want to say or ask or? Okay. Okay, so yeah, so this is just what we talked about so far. Yes.
Do you get a quantitative result from the DSDimension?
It is quantitative, but it's not sharp. The lower bound, if the dimension is d, the lower bound is d. The upper bound is d to the 1.5. There is a gap between the lower bound. Yeah. Mm-hmm. Other questions? Okay, and one other thing which I think is worth keeping in mind is that there is a local way to define dimension. We project and see what is going on in the local part. And there is also the option to bring computations into the picture and try to define dimensions using this idea. Okay, and now I want to tell you about three more specific things. So just three things. Yes? I don't know of any nice computational model that defines it. The question was, can the DSDimension be defined computationally? And the answer is, I don't know. So I want to tell you three more things, and that's it, I promise. One is just a way to, a learning game which is defined by a graph, which I think is just a nice mental picture of learning this game. So here is the learning game. We have some graph that we know. For example, the graph on the right-hand side in this picture. And then we get as input, as learners, an edge of this graph. How is this edge chosen? First, we choose some random vertex, let's say uniformly at random, or some other way, some other measure, but let's say uniformly. And then we choose one of the edges that touch this vertex. Okay, so we first choose a vertex and then choose an edge. But we as learners see just the edge, which is some noise of the true data, which is the vertex. Okay, so it's somehow it hides the thing we care about in a very clean way. And our goal is to guess the vertex. Okay, so this is a learning game. Somebody chooses a vertex, hides it with an edge, gives us the edge. Our task is to guess what is the vertex. So this is a nice way to hide information, and you can play it with other structures than a graph, but a graph is nice. And one thing that comes out of this mental picture is that an algorithm in this scenario is an orientation of the graph. We get an edge, we need to orient the edge to some vertex. So an algorithm is an orientation of this graph. This is the, yes?
Two questions. First, when you say random, what distribution of that part of the, what you don't know?
Let's say it's uniform. It's not so important. It's just a mental picture. It's not like...
Do you think algorithms are deterministic?
Deterministic algorithm is an orientation, and you can make it randomized if you wish, which is a distribution over orientation. Okay, so yes?
So you get a single edge, or you get...
A single edge, yeah, just a single edge. No, nothing, we can't collect data, just a single edge, guess the vertex. Okay, so And the thing about the DSDimension, which I find the DSDimension somehow captures this idea. The graph structure somehow tells us, do we have a non-trivial algorithm or not? This depends on the graph. How do we capture it? This is what the DSDimension do. So the DSDimension is a way to capture this in the learning setting. But let's focus on these two examples. If the graph is regular, like this, then we have no way to do something non-trivial. Like just the distribution on edges is uniform, nothing happens. But if the graph is a tree, we can do something non-trivial. We can direct all edges towards the root, for example. And then, if you think about it, you get a non-trivial algorithm. Because if we choose a vertex V, it is more likely that we choose edges that go down than an edge that go up. So on a tree, we can do something non-trivial, whereas on a regular graph, we cannot.
We're talking about infinite graphs here.
So this is just a finite graph. Yeah. The leaves are, as you say, have some, what I said has some issue on the leaves. Okay, so this is what the DSDimension achieves. It somehow captures this graph property. I will not say more. So the idea I want to keep from here is that there is this game on graphs, which is a model for hiding information, which is a nice model. This is the summary of this part. Now I want to tell you two more ideas. One is this one inclusion graph algorithm, which is a very, very general algorithm. And I want to tell you because I don't think, who knows what is this algorithm? Okay, so my guess was somehow correct. So I didn't know what is this algorithm until relatively recently. And I think it's a very, very nice algorithm. So I want to tell you this algorithm. So this is a learning algorithm. So what is this algorithm? As the input we get is the collection of functions h. This is one thing that helps us to guide our decisions. Then we get some collection of data we collected from h. So we get some x's and their y's, and the y's are labeled from some functions in h. So we have the concept class, and we get data labeled from this concept class. So this is the data we collected. And now what do we need to do? We need to make a decision on a new x. So somebody gives us also an additional x and tells us what is y. This is the input. What do we need to output? We need to output y, which is h of x. H is the same label of the previous y. This is the mental picture. So we get some data, we get a question, and we need to give an answer. Okay, does it make sense? Okay. And for me, how do you do that? It's not this is too abstract, but they found a very, very clever way and very simple way to do this. So here is the one inclusion graph. It has 4 steps. First, you define a graph. What is the graph? The vertices of, we have a collection of Boolean strings of length n+1. This is the projection of h to these n+1 points. Notice that these n+1 points have no y in them. We just project to the x part. Yeah? So we have some collection of n strings, Boolean strings of length n+1. And these are vertices of the n+1 Boolean cube. The Boolean cube has a natural graph structure where 2 vertices are connected if they differ in a single entry. So this is the standard graph structure. So we look on the graph that the Boolean cube induces on this vertex set. So we built a graph from the data. And this graph depends on the x's, but does not depend on the y's we saw.
And on H.
Depends on h, yeah. H tells us what are the vertices of this graph. Yeah. Now, the second part is we find an orientation of this graph with the property that every vertex has small out degree. We choose the best possible one, and here you need to argue that if the VC dimension is small compared to n, then you can do that. This is a non-trivial part, but you can argue. So we find an orientation of the graph. The graph did not see any of the y's. It is a graph, and we found some good orientation in the sense that the number of out degree edges is small. So this is the second part of this algorithm. The third part is interpreting the y's as an edge of this graph. The y's are all the coordinates but the last one. So this is an edge of the graph. And now we can use the orientation to choose a vertex and then output the value that is written there. So we output 0 or 1 depending on what we saw, but in a completely abstract way. So we built a general graph. From the data, we connected things according to neighbors. We found some orientation based on the amount of cleverness we have. And then we think about part of the data as an edge, the y's as an edge, and then we can make a decision. This is a very nice way to compose all of this information together in predicting the value of x. And this is called the one inclusion graph.
We're interested only in the orientation of one edge, right?
In this scenario, it is the orientation of a single edge.
About the other orientations of this graph, right?
Yeah, so the reason I stated it in this way is that to analyze the correctness of this algorithm, you need to have this property for all vertices. So you need to find an orientation that is good in every vertex, not just in the specific one you got as y here. But I did not explain the analysis. Okay, so this is the one inclusion graph algorithm. And the last thing I want to tell you about.
Can you say about this algorithm?
So this algorithm is a PAC learner. This is the property. It's a learning algorithm. It learns H as long as the VC dimension is smaller than the sample's complexity in some specific way.
Doesn't return a consistent hypothesis.
So this algorithm is not an ERM. This is correct. It's not even in the class H. There is no reason to think it's in the class H. Yeah. Somehow it finds an hypothesis outside the class in a very abstract scenario, like which is a. So the vertices have n plus 1 entries. Y1 up to yn is like the first n. So the last two values is an edge of the graph. So we think about it as an edge. Okay.
Actually, why aren't all the hypotheses consistent on y or something like that, or on the last one? No, but I'm saying why do we have the two vertices that are consistent with both labeling of y?
If there is no such thing, then we are done.
Yes.
Yeah.
So
Yeah. Mm-hmm. Okay, the last idea I want to tell you about is related to this Natar dimension, And I think this is a story by itself that I'll be happy to talk about and understand better with your help. So here's the picture. So there is a general equivalence between concept classes. In this case, there are two, the size of X is 2. There is the first coordinate and the second coordinate. So, and what is called colored simplicial complexes. So every function, 1, 2, 3, 2, 3, 4, and so forth, in H, comes with an edge of the graph. You see there is an edge 1, 2. There is an edge 2, 3. There is an edge 3, 4. The blue vertices are the second coordinate. The green vertices are the first coordinate. See, you start with a collection of functions and you build, in this specific case, a simplicial complex, in this case a graph, just a graph. So this is a picture of such an equivalence between some colored simplicial complex and the concept class. Does it make, yes? The numbers are elements of Y, exactly. Yeah, the vertices, exactly. The vertices of the graph are the alphabet symbols, are the elements in Y.
So what does 1, 2 represent? Which function?
1, 2 is the edge, is this
So
edge.
Function, for the first element it gives 1 and the second element gives 2.
Yeah, yeah.
So why each vertex has one color?
The colors is the coordinates. So when edge 1, 2, we have two values, 1 and 2. 1 is green, so it will appear in the first coordinate of the function. 2 is blue, so it will appear in the second coordinate of the function. The edge 2, 3, 2 will appear in the second coordinate, and 3 will appear in the first coordinate. So the colors of the vertices tell us in which coordinate do we put this vertex. So the blue vertices appear in the first coordinate, in the second coordinate, sorry. The green vertices, so the colors are not clear again.
But why can't there be a function that gives 1 and 3, then 3 would be colored with 2 colors?
So to make this equivalence full, you need to have 1 of the first coordinate, 1 of the second coordinate. You sort of duplicate Y's if you need. So this is an example of how a concept class translates to simplicial complex and vice versa. And one amazing property of this translation is that it translates information from the learning perspective into information that topologists care about in a direct way. So the Nader dimension being 1 translates to hyperbolicity. I can talk about it later. So it directly translates. Somebody defined this notion prior to without seeing the Nader dimension. Another thing that happens, the pseudo cube property translates to something related to being a pseudo manifold, which is again something that somebody cares about, like in a different context. So this translation of information goes to areas that was to an area that was studied before in a concrete way. So this is a very nice thing here. And so now I want to give you a few examples. This is an example of a class with Nader dimension being 1. There is no cube. In the graph, there is no cubes. There are no cubes. So the maximum size is an edge, 1 dimension. But the DS dimension is 2. It's words of size 2, where every word has a neighbor. So this is an example, a very simple example. This will take each of you 10 seconds to find, of a class with Natarjan dimension 1 and DS dimension 2. So this is a simple example. The next example is not as simple to find. This will take maybe a bit longer. Here is an example of a class with 54 words. The words are the triangles. And it has Natarjan dimension 1, and the DS dimension is 3. So it's a three-dimensional, it's a two-dimensional object. Every word has 3 coordinates. So the alphabet symbols, as Avi said, are the vertices in this graph, the things that have colors. The words are the triangles. Every word has 3 coordinates. Let's say the blue is the first coordinate, the green is the second coordinate, and the, I don't know what color, the square is the third coordinate. So every word has 3 coordinates, and every word has 3 neighbors, 1 in the first coordinate, 1 in the second coordinate, and 1 in the third coordinate. So this has DS dimension 3, and the Natarjan dimension is 1. And here, this is a finite object because we glued this edge to this edge. We glued this edge to this edge, and we glued this edge to this edge. So it's sort of a closed surface. So this is an example of a class of size 54 with DS dimension 1 and, Natarjan dimension 1 and DS dimension 3. It's a very nice picture, I like it. I don't know. I did not, what is the genus of this surface? And the suggestion was 2, and I don't know. There was a question? No? Okay. So we have 1 and 2, 1 and 3, 1 and 4. This is the picture. The smallest one we were able to find. It's a concrete thing, and the number of words is this large: 100,000, 18, and 98. So 6, 54, this. Okay, this is the numbers we have, and we don't know what, we couldn't find any with DS dimension 5. We could not. It's 2 at least. Yeah, this was done partly with a computer. So I will tell you what is known, and this is something very nice. These people, Januszkiewicz and Światkovsky, prove that for every dimension there is such a construction. Okay? They constructed it, and their construction is algebraic. How do you construct things? Use algebra. So they constructed. Actually, they provided a two different mechanisms to construct such things. And this is one of their papers. They have 2 papers. It's called the hyperbolic Coxeter groups of large dimension. And this is a quotation from their abstract. This is a symbol I should stop. Yes. Okay, so just random. This is, I just copied it from their abstract. I deleted some, they have these references in the abstract, so I deleted this. But other than this, I kept it word by word. What is written here, these objects are complicated. They are so complicated that they were first conjectured not to exist, and then they were conjectured to require difficult mathematics, but then we found them. Okay, so this is sort of what is written here. And their construction, in one word, it is very simple. What is this word? How do you construct something? By induction. Induction is the only, but they have an amazing induction. Like, I don't understand all of it. I'll be happy to understand it better if you want. I'll be happy to talk about it. They use properties that before I saw it, I could not understand how you can use such a tautology type statement to do something useful, sort of, but they actually used an amazing, it's a very, very nice, actually 2 ways to construct these things. So they found what we needed. So we just borrowed their, so, and this is also related to, so even this, without their paper, I do not think we could have even found this. This is too large to look for. Like, so we saw what they did and somehow collected information, and this is the only thing we could. Yeah, this construction is the reason that Natarajan does not characterize Pak learnability. The Natarajan dimension is 1, but this thing is not Pak learnable. Yeah.
The dimension is 4. Yes, dimension is 4.
Yeah, this is 4, but there is an infinite family. So, yeah, and this is what they did. Yeah, they did everything for us. Yeah. Yes.
The complete space is going to always be a hyperbolic manifold?
Yes. So what?
The genus was 2.
The genus was 2. Okay.
Because 1 is not hyperbolic.
Yeah, it's not 1. This I know. Yeah. Yes.
Do we know if there exists groups that have this
There is Natarajan dimension.
Natarajan dimension 1 and DSDimension of arbitrary size, or do we not know if?
Yeah, this is what, so I guess I did not write it explicitly. What these people showed is that for every D, there is a pseudo cube of Natarajan dimension 1, and the dimension is D. So arbitrary large D and Natarajan dimension 1. This is what these people proved exists. And another related thing is that this simplicial complex has a dual object, which is a Cayley graph, a simple graph. This is a Cayley graph with some number of vertices. In this case, it is a Cayley graph with 100,000 vertices, and the degree is 4. And the edges of this Cayley graph can be partitioned to 4 perfect matchings, because every generator is an involution in this scenario. It's a Coxeter type group. So we have a very concrete graph of degree 4 with 100,000 vertices. And there is a family of such graphs of degree 5, of degree 6, and they get larger and larger. And these graphs are very, very special. But we don't know of any reason to look at them except this reason. But I'm sure there are reasons to look at them. So this is another thing which is worth understanding. Okay, so this is it. I'm out of time. Yes. Thank you.
So any questions? Okay.
So you showed that family of functions it's like half learnable if the DSDimension is finite, right?
Yes.
So
So the question is, we show that the DS, so it has two parts. First, that the DS dimension characterizes Pak learnability. This was the first statement. And then the second statement is that for every D we have this graph. How do we prove that the DS dimension does not, or does, so the Natarjan dimension, sorry, does not characterize learnability. And we can take these pseudo cubes and glue them together, sort of in a disjoint type of way. The Natarjan dimension will still be 1, but the DS dimension will be infinite now when you glue the whole thing together. And this will tell us that no matter how many samples you choose, you will not be able to Pak learn it. So gluing somehow in an obvious, in like a non-interesting way, does the thing. Yes?
It seems from your lecture that the thing that measures the learnability is like an integer dimension.
Mm-hmm.
But I mean, there are measures of complexity which are not integer. Like we use in information theory the capacity of complex class, which is a number. It's not an integer, which again define the ability, the learnability. If the capacity is not is finite, you can learn, and it's also define the rate of learning. So that's one thing, not just dimension.
Yes.
The other thing I want to mention is that we know that there are classes that the dimension is infinite, maybe the VC dimension is infinite, like deep neural networks, right? Which we know that we can learn. So there is another notion of learnability which is not captured by this demand, if you want, for uniform convergence over all the things. So
yeah, so I will summarize, so I will not be able to repeat it word by word. So one thing is that dimensions can be non-integers sometimes, and one way to find non-integers is using information theory, which is also defined in an abstract setting, relatively abstract. This is correct, and I did not talk about this at all. And the other thing is that in some real-world scenarios, for example, when we have neural networks, the VC dimensions or other dimensions are very large, although in practice things are happening in a good way. And here the answer is that this theory does not explain this phenomena, which is correct, and it's one of the drawbacks for this theory. Yeah.
So let's think about it again.
Thank you.